Right, go ahead, Alex.
Cool. Hi, I'm Alex. This is my full name, but I go by Alex. So I'm a postdoc here. I got my PhD from UC Berkeley last year. My host here is Ariel. And today I want to talk about some problems that I thought a lot about the last 5 years in Berkeley. So the first part, or the 0th part of the talk is going to be introduction. So I'm going to talk a lot about auctions because there's been no auctions talk in this semester. So I'm going to make sure everyone is on the same page at least. I'll keep my proofs to a minimum. So part 0 will be introduction. Part 1, I'll talk about a paper that I had with George Pierakos. So George was a PhD student in Berkeley. He then worked for Goldman Sachs, and now he's working for an algo trading company. Aviad, he was also a PhD student at Berkeley. Now he's at Harvard for his postdoc, and then he'll be joining Stanford. And if you don't know Christos, shame on you. And the second part of the talk, I'll be talking about a paper that's going to appear in SOTA 2018. My co-author is Siki Liu. Siki is an undergrad. She's actually applying for grad school. Hint, hint, hint. Applying for grad school. Okay, cool. So that's the plan. Again, proofs to a minimum, so interrupt me all the time. Okay? Cool. So let's start. So typically, a problem that a lot of people in this room have thought about, or the problems a lot of people in this room have thought about, have this type of structure. You have some input, you have some desired output, and the thing in between we call the algorithm, right? So designing algorithms is something we do a lot in computer science. So the type of problems that we're going to talk about today are problems where the input we don't get for free. So the input is controlled by some selfish agents, and they report the input to us, and they have preferences over the outcomes. So the thing we want to design now, we call the mechanism. And of course, the challenge is to incentivize the agents to behave honestly. Okay? So mechanism design, the design of mechanisms, can roughly be split into two very big buckets depending on how you can incentivize the agents. So if you have money that you can use to incentivize them, you have mechanism design with money. And if you don't, you have mechanism design without money. And without a doubt, the king in mechanism design with money is the auction. So everyone is thinking about designing auctions. And there's millions of applications. So Google ad auctions, Kayak, Uber, pricing resources at EC2. So there's many, many applications of the types of results that are proven in this bucket. In this bucket, people think about cake cutting, voting, kidney exchanges, and so on. Okay? Where money is either illegal or immoral, and so on. That you can't start paying people to vote how you want them to vote, right? Good. So this talk is going to be about auctions. So far, so good. Good. So part 0, single item auctions. So say you have this item that you want to sell, and you have a bunch of agents. And each agent has a value for the item. And that value is secret. Okay? You don't know the value. And an objective you might have is just to give it to the person with the highest value. So in algorithm design, this is the maximum, find the maximum algorithm, right? Find the max of n numbers. Very easy algorithmic problem. But if you don't know the numbers, how would you approach this? Well, the first idea you might have is just run the find max algorithm, right? So just ask them for their values. So you ask, and the first agent says, 50. And the second agent says 100. The third agent says 10 to the 100. So this very fast becomes a race to the top, right? Who can say the highest number? Good. So, okay, that's the first idea you might have. So the problem, of course, is incentive, right? So if everyone wants the item, just go crazy. So William Vickrey solved this problem for us in 1961. So he got a Nobel Prize for it, by the way. And the solution to this problem is the second price auction. So you give it to the person that says the highest number, and you make them pay the second highest number. Okay? So if this is what happened, Pikachu would win and would pay 100. And notice that this is a bad outcome for Pikachu because he's only willing to pay 5. He's paying 100. Good. So a very easy calculation. So now the agents are happy, and they all say the truth. And Pokeball goes to Pikachu for a payment of 3, which is the second highest. Question?
But what if first say $3? second say $1 billion, it means that he automatically wins.
Yeah, but he has to pay more than he's willing to. I mean, so you're saying this 2, I would change to a billion.
Yeah, 2 is 5.
2 is 5.
So I mean, there is no second. The first and third.
Okay, so this one says a billion.
Yeah.
Yeah, I mean, but they don't pay any cheaper.
But he pays 3.
Yeah. So the payment doesn't change. So why not say 5? You're not going to change your.
There are another examples: 3, 4, and 5.
Okay, 3, 4, and 5. Good. So
he does 3.
5 would win and pay 4.
No. He does 3. The second tells billion.
Okay.
5 would win.
What's the real value of a billion?
4.
4. So the 4 wins and pays 5. Because that's the second price in this example, right? 3, a billion, 5. The second price is 5, which is more than 4, or whatever you had. Good. So this auction incentivizes everyone to behave honestly and manages to give the item actually to the person who values it the most. So good job, William Vickery. Here's your Nobel Prize. Excellent. So that's the first question.
So before we move on, why doesn't the dumb thing of make the person pay exactly what they did?
Good. That's a great question. So again, to rephrase it, the question was why can we just say pay what you say? Because then people will start doing things like, oh well, I won with 5, but I could have won with 4, maybe. So then you start like playing around. So there's this theorem that says that if you do this thing again and again and again, the equilibrium behavior is the same. So if you repeat this game, you will end up with like this person saying 3 plus epsilon and paying 3. So I want to think of auctions where you just incentivize to say the truth. So if you pay what you say, the winner is not incentivized to say the truth. Good. Excellent. So first objective you might think of is give it to the person who wants it the most. The second objective you might think of in this money setting, especially if you have applications in mind like ad auctions, is maximize revenue. So make as much money as possible. Okay, good. And this is a challenging problem even for one agent. And here's why. So here's something you might try. You might say, like, I'm just going to tag a price on this item, and they can buy or not. Right? That's a natural approach. So say you say, okay, this is $10. So this is a good idea if the value happens to be 11. It's a bad idea if the value happens to be 11 million. And it's even worse if the value happens to be 9, because you're not even selling it. Okay? So I guess the observation here is that different auctions do different on different inputs. So kind of this problem as its own is a little hopeless. Like we can't, have any results in some sense, or we can't like talk about the guarantee of our results. So how we'll think about maximizing revenue is that we'll think of the Bayesian setting. So instead of having just some value, we're going to think of the value as being drawn from a distribution, and we'll try to do well in expectation. So we're going to have a known distribution D where the value is drawn from, and our objective will be to maximize expected revenue. Okay, and the person who solved this problem was Roger Myerson in 1981, so 20 years later. Also got a Nobel Prize. So 2 out of 2. Good. And it does happen to be that the optimal auction imposes a price. It just depends on D. So again, the input to your problem is a distribution, and you know that you're going to be faced with an agent that draws value from that distribution. And there's a price that you can find that depends on D, that's optimal. Among all possible scenarios where you just interact with the bidder and so on and so forth. Go ahead.
Do you need any assumptions on D that are?
No.
So it could be any?
Any distribution. Yes. Good. And in fact, Myerson solved the problem for a more general case where you have independent non-identical distributions and n agents. So the setting is you have n agents, each has their own distribution, they draw values, and you want to come up with a way to sell the item.
So like why not just make the support of D1 and just like totally get around like the Bayesian side of things?
You don't get to decide on D. D is the input.
Oh, okay, all right.
I mean, if the support of D is 1, that means I know the value. So that's a trivial problem. Good. Questions?
What if you only have access to D through some Oracle?
Good.
This would be like poly,
in
supported
Oracle.
system, right?
What do you mean by Oracle?
You can just stamp the stuff from D.
Oh, good. So now you're jumping ahead, like, I guess 30 years later. Tim Roughgarden asked that question. So there are many recent results, like recent in the past 5 years of this nature. So if I only have sample access to D, what can I do? And there are many, many nice theorems on this. Right? Like if you're interested in like a constant approximation, or if you're interested in like 1 minus epsilon approximation of op, there's many results in this form. So we know good answers. And then you do have to make some assumptions on D. That they're not like, basically they have small tails. Otherwise, like kind of anything is. Okay, good, great question. Cool, good. So this brings us to the problem we're going to study. So we're going to study dynamic auctions. So here's the problem that we'll be thinking of for the rest of the talk. So I have an item that I'm selling now to a buyer with a known distribution, D1. And tomorrow, I know I'm going to sell another item. And, tomorrow the agent has evolved somehow. So they might have different values. So if they evolve a certain way, they have a value v2. If they evolve a different way, they might have a value v2 prime. And these happen with certain probabilities, right, depending on the outcome on the first day. So probability third, you have v2. With probability 0.7, you have v2 prime. And then I'm going to sell a third item. And again, more evolutions will happen. And depending on the history so far, you might have different probabilities of the values in this stage. Okay, does that make sense? So I guess Pokemon might not be a good example. So think of like selling a phone, right? So Apple wants to sell you the iPhone today. They know, you buy iPhones, like you're going to buy one in 2 years. So they know that but in 2 years from now, you might be willing to pay a different amount, depending on how much you're willing to pay today. Okay, then 4 years from now, different iPhone. And depending on what happened so far, different value with different probabilities. So here's the formal model. I'm going to write it on the whiteboard as well. So we're going to have M stages, just as a cheat sheet, N agents. So one item is sold at every stage. And the value you learn at the beginning of the stage. So you walk in stage 1, you learn your value for the first item. You don't know your value for the second item. You walk in stage 2, you learn your value for the second item. You don't know 3, 4, and so on, right? And xik will be the random variable that tells you the value of agent I for stage k. Good? So Byron learns the value at the beginning of stage. So xik can be correlated with xik in prime. So we allow correlation between stages, but we want independence between agents. That makes sense? So my value for xi4, my value for the fourth stage could be correlated with x1, x2, and x3, but is independent of the values of other agents. Okay? Good. And our objective will be to maximize revenue. Question?
And just to clarify, like xik is also independent of like xi prime k prime, right? So it's like it can't be like I saw.
Yes. Yeah. Sorry, my notation is a little weak. Yeah, xi prime k hat. Yeah. Yeah. Great. Good. So our objective will be to maximize revenue. And then now let's think about the constraints a little bit. So a first constraint is participation guarantees. So in some sense, notice that earlier it was too obvious to even point out, but I never made anyone pay more than their value. Like when someone said, I'm willing to pay 10, I didn't say, oh great, it costs 100 and I'm forcing you to buy. Okay, so I'm going to keep the same guarantee. So I'm never going to force anyone to pay more than they're willing to. So your expected payoff from participating should be non-negative. Okay? Good. And the second constraint is truthfulness. So I want to, again, incentivize the agents to behave truthfully. So that was the whole point of this business. And this is a little tricky, right? So what is truthfulness in this setting? Like it's so many things are happening. How would you even think of truthfulness? And the complication is that the outcome on stage K might depend on what happened on some other stages. right? So the outcome on stage 3 might depend on what you said on stages 1 and 2. So when you're deciding on what to do on stages 1 and 2, you should think of how that will affect you on stage 3, and so on, right? So in some sense, every agent makes this like following a thought experiment. So if my value today is v, what will happen if I reported v prime? And then tomorrow, if the truth is like v2, maybe I'll say v2 prime. But if the truth is v2 prime, I'll say v2 double prime. And if the truth is v2 double prime, maybe I will say v2 double prime, and so on, right? So when you're thinking about what to do, you're kind of considering a deviation strategy from things that might happen to things that you will say happened. So, a mechanism is truthful if basically you want to say the truth even after considering all the deviation strategies. Does that make sense? So, let's see. So you want to maximize revenue. Subject to, I will call this IR. So individual rationality. This will be the thing that says I don't charge you more than you value. And here I want to say that for every stage k, for every history, from 1 through k minus 1, so whatever happened, for every value you might have now in stage k, for every value you might say now vk prime, and for every strategy from, future realizations to future reports, I want to say that truth is better than lie. Okay? Very hand wavy. Those are the constraints, and I guess I'm doing this business to show you that even for k equals 2, on the first day, when you're thinking of what should I do tomorrow, you have exponentially many options, right? Because you're having a constraint over all functions of what will happen tomorrow to what I should say tomorrow. Okay, so even for k equals 2, this problem is like super exponential, right? Because I'm writing a constraint for every function. Good? How many people have I lost so far? Okay, good. Excellent. So part 1, computational complexity. This is Aviad, this is George. Again, if you don't know this person, shame on you. Okay, so we're going to talk about the computational complexity of this problem. So, what could the optimal auction look like, even for a single agent? And let's assume independent stages for now. So my value today is independent of my value tomorrow. Here's a good auction. In the first stage, when you walk in, you know your value, and I know the distribution where you drew your value from. I can just do the Meyerson thing, right? I can just do what Meyerson would do if this was the only stage possible. So I sell you the first stage optimal, and I say, wait, before you go home with the item, just pay me your expectation for all the future items, straight up. Right? So I get a grad student here, I'm like, you look like you'll get a position to be a professor soon. So why don't you just buy the next 10 iPhones at the price you would be willing to pay if you did become a professor. In expectation, this is fine, right? The expected utility you have is non-negative. Because in expectation, everything is fine. You're not paying more than you're willing to. But, in some sense, you're kind of robbed at gunpoint, right? So pictorially, this is what's happening. So you have an insurance company or something, and, just ask you to pay all your money. So this, I guess what I want to say is that this is a good auction if you're the government or like, an insurance company or something, but you can't pull this stuff if you're Google or Uber. You don't walk in an Uber and they say, well, just pay me for all your future rides. Or no future rides for you, okay? So in some sense, I want to strengthen the participation guarantees a little bit to get reasonable things at the end. Does that make sense? So I'm going to ask for ex post individual rationality. So that means that at every stage, you should have non-negative utility, no matter what. So that prevents me from doing these tricks where I make you pay now for something for tomorrow. Because I want no matter what happens tomorrow, your utility to be non-negative. So that means that if 0 is in the support of all distributions, I can never force you to buy now something for tomorrow. Does that make sense? Questions? Cool. So our new goal will be to maximize revenue. And instead of participating, instead of IR, we're going to have ex post IR and truthfulness. Okay? Good. So, okay, as computer scientists, we might ask, can we find the optimal dynamic auction in like polynomial time and whatever? And our first theorem would be that yes, we can. So the optimal auction can be computed in time polynomial the number of types, the number of stages, and for a constant number of buyers. And typically the number of types is exponential in the number of stages. But notice that, as I pointed out earlier, this is already surprising, right? So what we said about writing a constraint for every function, those are functions from values to values, types to types. So it's kind of surprising that this is not already exponential in the number of types. So you need a lot of like tricks to reduce the exponential of the number of types that you would get by just writing down deviation strategies to something polynomial. Okay, but I won't get into the details of how this works. But I just want to point out that this is not a trivial thing. It's not an easy thing to prove. But after you prove it, you might look at your solution and say, well, is this a reasonable thing? So I managed to find this optimal object in polynomial time, kind of. Is it an object that I'd be comfortable giving to Google and ask them to run it? Okay, so in some sense, what are these ex post IR auctions capable of? Okay, and I'll show you an example that shows us they're a little bit crazy, so they're a little bit unreasonable, even subject to this constraint. So let's see the example. So I'm going to have two independent rounds. So my value today will be independent from my value tomorrow. The values today will be distributed as follows. So you're going to have a value 2 to the I with probability 2 to the minus I for I 1 through n. Okay, and the remaining probability goes to 0. And tomorrow is going to be the same structure, only I will go from 1 through 2 to the n. Okay? So again, I want you to be truthful, and on no stage can you charge me more than I'm willing to pay. Great. So something you might think of doing, something you might think of comparing yourself against to, especially since the stages are independent, you might say, I'll try to do Meyerson and Meyerson. So I'm just going to ignore the dynamic nature of the problem altogether. I'm just going to pretend these are just two static problems that are happening one after the other. I'm just going to see how I do. So an easy calculation shows that this is the total revenue you make is less than 4. Here's why. In stage K, for K1 or 2, no matter what price you set, you cannot make revenue more than, the revenue you make is actually exactly equal to 2 to the P, for price P, times the sum from I greater than P to the minus I, which is less than 2. Right? So if you set a price of 16, the probability you sell is 1 over 16 plus 1 over 32 plus 1 over 64 plus blah, blah, blah. That, 16 times that is less than 2. Cool? So 2 plus 2, less than 4. Great. So here's a really crazy dynamic auction. It's going to be randomized. So now I'm going to charge you whatever you say. So if you walk in and say, I'm willing to pay 2 to the P, you're going to pay 2 to the P now. And tomorrow, you're going to get it for free with this probability. Whatever you set over 2 to the n. Okay? Let's see why that is truthful. So say, instead of your true value R, you said something else. Sorry. Instead of Ri, yeah, you said something else. You said R. So if you say R, your future utility will be R. Because your future utility is just whatever you said over 2 to the n times your expected value for the future item, which is 2 to the n. Sorry. Everyone gets this? So this distribution has expectation 2 to the n. So if you say I'm willing to pay r, then I'm going to say, well, tomorrow you'll get it for free with probability r over 2 to the n. So multiply by 2 to the n, that's just r. So let's see about your today's utility. So today's is just v minus r. So v is the truth. Minus r is what, what you report. Plus r for the future, so it's just v. So no matter what you say, your total utility is your true value. So you might as well say the truth. Again, let's see it more carefully. So the auction is, you pay what you report, you get it for free. The future item you get for free with a report over 2 to the n. What's your value now? Your true value minus your report. This is it. What's your utility for the future? It's just whatever your report was. V minus r plus r equals v. Okay. So, question?
So if you don't get it for free in the future, you don't get it at all?
Yes, yes. Good. Yeah, if you don't get it for free, you don't get it at all. So I'm just going to say, tomorrow I'm just going to flip this coin, and if it lands heads, you get it. If not, bye-bye. Okay. And what's the total revenue? The total revenue is the expectation for the first stage, which is n. So it's n versus 4.
But don't you need multiple items? Or this one person?
One person, 2 items, 2 stages, right? This is the kind of the smallest example I could construct in my setting, right? So n versus 4. So in some sense, what is this saying is that by ignoring the dynamic nature, you're unboundedly far away, even for independent stages. So if you ignore that this is, if you treat this as 2 problems versus 1 problem, you're losing a lot. And also it's showing that you can do crazy things even with ex post IR auctions. Cool. So in some sense, we kind of proved all these things, but that was not our goal. Like, our goal was to be Meyerson. So what we originally had out to do was to have this very strong positive results for this setting. So we wanted to say, Meyerson's result is so great because, the setting is simple and it gives you this very powerful positive result. So the question we really want to ask is there a very, very powerful positive results for these dynamic auctions? Okay, so is there a Meyerson's theorem, so to say? And if not, how would you prove such a thing? So how would you prove that there's no very strong positive result? So this is kind of the premise of the paper we had with Christos, Aviad, and George. And our premise is, if you believe this, so if you believe that nice theorems imply efficient algorithms, and remember we're looking for structure, right? We're looking for structure in the problem. And if there exists a structure, there will be good algorithms. So if you believe this, then you should believe the contrapositive, which says that if there are no efficient algorithms, then there is no structure. So if there are no efficient algorithms, there is no Meyerson's theorem, which is a structure we're looking for. So you can see, and statements of this form we are really good at, as opposed to economists. So no efficient algorithms is, NP hardness for us. So where am I going with this? The question we really want to ask now is there a reasonable auction that we can compute? Because all these auctions we computed so far are not really reasonable. And I'm going to just add another constraint. So I'm going to ask, let's just make it deterministic. So let's just say that if I had a really powerful positive result, and it gave me auctions that I really liked, those auctions would have been deterministic. Because those are the auctions I like. They're not super weird. And kind of the main theorem of this paper was that it's NP hard to compute the optimal deterministic auction in this setting. Questions? Good. So this, in some sense, I would like to say that it implies that, if there's a very strong positive result somewhere out there, it doesn't give you deterministic auctions.
Alex, what's the size of the input? The size of the distribution for?
So this is NP hard even for 2 stages. So the input is n numbers for the first stage, and n squared for the second stage, right? Or n times m.
Meyerson's result is sort of very practical because it's a posted price. Do you have a feeling what deterministic optimal auctions look like on examples? Or in what sense are they not really?
Good. So there's a lemma before the theorem that says that deterministic auctions in this setting look like two posted pricings. So the deterministic auctions that are optimal look like if you tell me value today, I'm just going to give you a price for today and a price for tomorrow. So tomorrow I don't ask you to report anything else. Good. Yeah. So thanks. Good. Cool. So what has our life so far has been? So we're looking for a nice optimal auction. That was our goal. And we found that we have to go through the hell of computational complexity. But maybe it's worth it. There's fast LP solvers, fast integer programming solvers. Maybe this is a task is worth doing if the result at the end is worth it. So I won't go into details in this talk, but in the paper we actually had more problems with optimal auctions. So optimal auctions are very sensitive to the ability of the seller to commit. So far I have assumed that I can just tell you, and here's what I'm going to do tomorrow, and here's what I'm going to do in the third stage, and here's what I'm going to do in the fourth stage. So if you remove this commitment power from the seller, all types of crazy things start happening that involve communication between the seller and the buyer. And kind of even worse, like a little bit the elephant in the room is, how do you know these distributions? Like, Myers result carries through because if you think of ad auctions, you say, well, I have all this data that I kind of know this distribution. I have a really good idea of these distributions. Like, how can you with a straight face say, I know X10? It's X1 now, and I kind of know details about X10, the distribution for stage 10. Like, how would we do something like that in practice? Okay? And not only the distribution, but also the correlations within the distributions. Like exact correlation between X1 and X2 and X3 and X4 and so on. Good, so that's the first part of the talk. So this sad Christos. So in the second part, the joint word Siki, we're going all the way to the other end. So we're going to be talking about simple auctions, approximations, and all the auctions we're going to talk about will make sure don't depend on the distributions. Okay, good. So join word Siki. So in the first part we're trying to be Meyerson. In the second part we're going to try to be Buller and Klimper. So let me tell you about Buller and Klimper, about these two economists. So this is one of the most beautiful positive results in auction theory that I know. So in terms of how do economists compare auctions, right? They don't have approximations. So how would they compare like Meyerson's auctions versus a second price auction, for example? Right? They wouldn't be able to say this is like a two approximation of each other or something like that, right? So here's how they compare it. There's this theorem that says if you have one more buyer, actually let me read it first. So the revenue of a second price auction with n plus 1 buyers with valuations drawn from mildly regular distributions, don't worry about that, is at least that of the optimal for the distributions for n buyers. So regularity is some tail condition, don't worry about it. But this is what this is saying that the optimal for n agents coming from a distribution X is smaller than Vickery, so second price, from n plus 1 from X. Does that make sense? So we call these resource augmentation arguments, right? So in some sense, it is better to get one more person to show up than learn X. Because notice that Vickery, second price auction, does not need to know X. You don't need to know the distribution to run it. So this theorem is saying if the distributions satisfy this condition, regularity, which is like any distribution you know kind of satisfies it, or any distribution I know satisfies it, let me not put the words in your mouth, then kind of you're better off getting one more person to show up than investing in learning what the distribution is. Good, does this result make sense? Cool. And notice that Vickery, the second price revenue is just the expected second order statistic, right? So it's the second maximum of n plus 1 samples. This is going to be relevant because I'm going to be talking about these a lot. Right, so I draw n plus 1 samples from a distribution X. I'm looking at the second maximum. That's the revenue of Vickery. So they showed that this is better than opt for n people. Great. So I'm going to try to copy this. So now I want to be these people.
So this is like a with high probability of this?
In expectation. Yeah. So in expectation over the distribution. So I don't know the distribution, but if you can guarantee to me that it comes from this family, then even if you knew it and you designed the optimal auction for it, I'll still beat you if I get one more person to show up. In expectation. Everything is in expectation. Good? Good. So I want to have a theorem like this for our dynamic setting. So what do I want to have? I want to ask, how many people do I need to make to show up every day? So I'm going to have C extra people. They're going to be showing up every day. And I just want to beat optimal. The optimal insane auction that's like the deterministic is going to be hard to compute. And the randomized I can do, with an insane algorithm and so on, right? This object. Like I want to beat this object. Good. And how many for an alpha approximation? So we call this number the competition complexity. So the Bülow-Klemperer theorem in this language would say that the competition complexity for a static single item auction is 1 if the distribution is regular. Right? Because one more agent, C is 1, one more agent, you beat optimal. Good? And the distributions I had earlier, the 2 to the I, probability to the minus I, are regular. So if I gave you like 10 minutes, which I don't have to think about it, you will see that regular distributions are kind of not good enough. So I'm going to restrict the class of distributions a tiny bit more. Okay? So my goal again is to solve for C. So how big C should be to beat optimal, subject to a distributional assumption. Okay? And this would be great, right? Because this would say, if I run a second price auction at every stage, I'm doing really great. I'm doing better than if I knew all the distributions and their correlations, and also it was cool to like run an insane auction on this. Cool? Cool. So this is going to be my goal. So, great. So how would you prove a statement like this, just to begin with? Well, you have the optimal auction for n buyers. So first we want to show that this is smaller than some benchmark. And then we want to show that the benchmark is smaller than the second price auction revenue for n plus C buyers. Okay? This is going to be the proof approach from 100 miles ahead. But the two steps are very disconnected. So you don't really, you could do one without the other. So for this step, for getting the benchmark, we're going to use duality framework developed fairly recently by Yang Chai, Nikhil Devanur, and Matt Weinberg. So I don't think, I shouldn't push it, but let me tell you the general idea of how you would prove such a thing in a little bit. And the second part will just be probability. So straight up probability. So I'm just going to prove stuff about bounds on expected order statistics. And for these to work, I'm going to use distributions for monotone hazard, that have monotone hazard rate. Okay? So that essentially means that 1 minus f is log concave. And all distributions are like that, like uniform, exponential, normal. Like this is a very big family of distributions. Okay? So I'm going to need this assumption for this step to work. Good? So 2 disconnected steps. Let's see the first one. So what kind of upper bounds do we have? So if opt nmx is the revenue of the optimal auction for n buyers, m stages, when the buyers' values are according to x, this complicated object, right? So these are the marginals, and I'm also omitting the correlation between them. So opt is less than the sum of expected max. So the optimal for m stages and n people is less than the sum over all stages, the expected maximum of n samples. Right? So this comes directly from participation guarantees. So this is saying this is essentially saying you can't charge more than I'm willing to pay, more or less. If the distributions are independent, I can do a little bit better. So I can take one of the distributions, I can take one of these objects and put it down to Meyerson. So instead of having expectation plus expectation plus expectation, I take the biggest one, or not the biggest one, I take one and take it down to Meyerson, which is smaller than expectation. And I can do this for any choice of k. So it's smaller than the minimum. Good.
If they're independent, why can't you run Meyerson each of them?
Because we know that is really bad, right? Meyerson, that's a lower bound. But earlier we saw that you can do expectation. So so we have a lower bound of expectation, and I'm saying an upper bound of expectation plus Meyerson. So you can't. So that kind of that example kind of shows you can't improve on this too much, in fact, at all. But yeah. Good. So these are the upper bounds on opt that we're going to work with. Really roughly how the duality works is as follows. It's very hand wavy. Actually, yeah. So you have so you write this linear program. So let me show it for like the static setting. So the linear program you might write looks like this. So sum of overall values, probability times the payment, right? So this is expected revenue. And you have, IR constraints and truthfulness. So truthfulness looks something like, for all v prime, so this is your utility, value times the probability you get the item minus how much you pay is bigger than your true value, your probability if you say v prime, minus how much you pay if you say v prime. So this is what the truthfulness constraint looks like. Okay? This is your objective, and you have the IR constraint. So this whole duality framework basically takes a partial dual. So you Lagrangeify these constraints, and you push them in the objective. Now once you Lagrangeify the constraints, the game you play, so you introduce a dual variable lambda v prime. So once you do this step, what happens is, very high level, that if you factor out the payments, their multiplier must be 0 because there's no constraints on it. So you're playing a game of pick lambdas, and then the adversary will pick x and p's, and that will be an upper bound on the objective. And the lambdas must form a flow in a certain graph. So that's kind of a very, very high level idea of what's happening. So it's a combinatorial argument of this type of object that comes from Lagrangeifying a program like this, in fact, this crazy program, and making a bunch of observations. Okay, so that's part one. Part two is just a bunch of bounds on the expected order statistics. So why were MHR distributions a good candidate for us? Because we knew things like this, right? So we knew the expected second max is bigger than Meyerson for one more sample. And we knew things like the probability that you're above the mean is more than 1 over e. And we knew also things like the contribution to the expectation from values that are really high is really small. So this is the integral from t to infinity, t times f of t. So we knew things like that, so this made them good candidates, and the statements we do prove look something like this, right? So we prove that the second highest of 4 n samples is bigger than the max of n samples. So saying if I draw n samples from an MHR distribution and look at the max, that has some expectation. That is smaller than draw 4 n samples from the same distribution and look at the second max. Okay, and this was the bottleneck to our paper, in fact, this statement. And we also, for the approximation, we prove something like this. So one more sample gets you a 1 over e approximation. No samples gives you a 1 over 3 approximation. Good? So just plug and play the two different sides of the bounds. And our overall theorems look like this. So if you have n buyers, m correlated stages and all the marginals are MHR, then the computational complexity is at most 3n and at least e minus 1 times n. The 1 over e computational complexity is 1, and the 1 over 3 computational complexity is 0. So again, this is like the tough one. What is this saying? This is saying instead of, if you can guarantee to me that the marginal distributions have monotone hazard rate, you're better off trying to recruit, a lot more people, have a lot more people show up than what you would do if you happen to know exactly all the distributions and all their correlations, and you had the ability to run insane auctions on this input. Okay? And if you strengthen the assumptions over here, if you add independence, then you can relax the marginal assumption and get one MHR. So you can get rid of, instead of m MHR distributions, you have m minus 1 MHRs and 1 regular. And I guess I didn't write it, but 2 regulars are impossible. So if you have 2 regular distributions, even if they're independent, all these numbers will be infinity. Okay? Question?
So is it below Klumpner?
Yeah.
So in that theorem, the additional buyer has to be identically distributed?
Yeah.
Okay. And here, do the additional 3n buyers have to have just MHR distribution?
Good. So that's a great question. So the question is, originally the theorem said everyone has the same distribution. I just add one more person with the same distribution. Here, I have all these correlations, so what is happening? What we're asking is that before the game starts, everyone has the same distribution. But once you start drawing, you can start having correlations. So like if I look at your, before we start playing the game, I know something like your first day is like uniform 0, 1, and your second is uniform 0, 100, and there's a certain correlation. I asked like 5 people to show up, they have the same type of distribution, but once we start drawing, like now everything goes, right? Now your marginals are not identical anymore. Yeah, so that's the condition. Thanks. Cool. So, okay, the conclusion. So we're studying this problem of selling m items in m stages to n agents. So without the ex post IR constraint, we ended up with like crazy auctions. With the ex post IR constraints, we could compute the optimal randomized auction, but it was a little funky. And if we added the deterministic constraint, we couldn't compute anything, even for 1 agent and 2 stages. And also for optimal auctions, we had other issues. So something like, I didn't go into it, but something like communication complexity shows up. And then in the second part, we talk about extra competition and second price auction at the stage, and we got a bunch of nice positive results, but we needed the marginals to be MHR. That's it. Thanks. Questions?
I'll ask a clarification question then. For the last theorem you stated, this might be sort of what Ellen was asking as well, but do you allow the different agents, are the agents allowed to have different distributions, or is it like a single fixed X?
So they're the same before we start. But once we start, so notice that once you draw your first day value, your second day distribution condition on that is different. But before we draw, I want everyone to be identical.
Okay, that makes sense. So
Yeah.
could you say anything about like what if they aren't all the same? Is this kind of hopeless? Because I guess you need to add more buyers, and I mean, what would their
Yeah, so in fact we do like the first part of the approach where opt is less than benchmark. I can get a benchmark if I ask for like stochastic dominance of, oh sorry, that was, if they're not identical, no, I don't know how I would say something.
Yeah, I guess
there are some theorems like that in the static auctions world that I don't remember, but they are somehow they depend on the support of the distributions and so on, or maybe you need like extra buyers from every single one, right? So if I have 5 buyers and they each have their own distribution, and I'm asking for how many extra, perhaps I need like 1 from every type or something like that, right? Or in some sense you wouldn't be able to avoid it because maybe you get all your revenue from like a certain distribution. So you should get extra agents from that as well.
I see, yeah.
Yeah.
You know something about the gap between deterministic and randomized, like in the setting?
Unbounded. Yeah. Like, yeah, log n or something for any n, yeah. Either way, like any adaptive, non-adaptive, deterministic, non-deterministic, the gap between randomized and expectation. So there's like these three things, right? Like Meyerson and Meyerson, deterministic, randomized, expectation, and unbounded gaps between any single pair. Yeah.
So can you say anything about the optimal value for n and n plus 1 players, how they relate? Like if n is large, should this be...
N and n plus 1?
Yeah. Should this be...
Sorry, are you talking about the expected max or?
Opt, yeah.
Opt.
Yeah, n versus n plus 1 for this kind of distribution.
I mean, opt for n plus 1 is less than second price for n plus 1. And I know that's 1/3.
Sure. No, so what I'm saying is, I mean, you're saying that...
You're saying without the MHR assumption?
No, with the MHR. Can you
With
say-
the MHR, that's a third already. I got that from this, right?
No, I'm comparing the optimal...
Yeah, so I'm saying opt, here's my proof. I know that, second price with n plus 1 is a third of opt of n. And I know that this is less than opt of n plus 1. Proof done. This is what I had.
No, I was wondering if you had something...
Better. No.
Because, I mean, if you could say that, then basically you're saying for large n, you don't get a 1/3 approximation, you get a 1/e, roughly, right? And if you could say that opt n and opt n plus 1,
Oh, I
by
see.
like 1 plus minus a little over 1.
I see. Yeah, I don't know. That's a good question. Yeah, but that's the best I know.
Great. No other questions? That's it.